Good day, students. My name is Adeshina Oladele, your physics teacher. I welcome you all to the class. The topic we shall be considering this day is fundamental and derived quantities and units. Fundamental and derived quantities and units. That's the topic of consideration today. We shall be dividing this lesson into subsection. 1. Fundamental quantities and units. 2. Derived quantities and units. 3. Dimensional analysis. Yes, these are the 3 subsections. The topic today is divided. At the end of the lesson, you should be able to define the fundamental quantities and units. Also, you should be able to define the derived quantities and their units. More so, you should be able to give examples of the fundamental quantities and their units, as well as the examples of the derived quantities and their units. Lastly, you should be able to solve some mathematical calculations with the dimensional analysis. Now, to start with, what is fundamental quantities? Fundamental quantities are basic quantities which are independent of other quantities. Fundamental quantities are basic quantities which are independent of other quantities. On the other hand, fundamental units are the basic units. Fundamental units are the basic units of the fundamental quantities. Of the fundamental quantities. You can see they are the basic units of the fundamental quantities, which are used to express other units. Yes, they are used to express other units. Now, what are the examples of the fundamental quantities? I will quickly highlight to us, to everyone here, the examples of the fundamental quantities. We have the lengths. We have the lengths. The quantity, the lengths. One, the lengths. And its SI unit, or the basic unit, is meter. Meter. Why its symbol is M. So this is the quantity. The quantity, the SI units, and the symbol for the fundamental quantities and units. The second one is the mass. The mass, the SI unit, or it's measured in kilogram. And the symbol kg. We also have time. Time measured in seconds. That is its SI unit. X, which is a symbol. The fourth one are the fundamental quantities. Don't forget, they are the basic quantities which are independent of other quantities and cannot be derived from other quantities. The fourth one, electric current. The electric current, which is having its SI units as ampere, symbol A, the SI unit. Then we have thermodynamic temperature. Thermodynamic temperature. The thermodynamic temperature has its SI unit to be Kelvin, K, as its symbol. So these are the fundamental quantities. Like I said, they are the basic quantities which are independent of other quantities and cannot be derived from other quantities. Now let's look at the derived quantities very quickly. The derived quantities and their units. The derived quantities, like I earlier said, the derived quantities are quantities derived from fundamental quantities. The derived quantities are quantities derived from fundamental quantities. The derived quantities, we have area. They are derived from fundamental quantities. And they are basic quantities using simple mathematical calculation. As in area, we have meter squared. Area, we have meter squared. Look at it. Area, meter squared. Why its symbol is m raised to power 2 meter squared. Then we have the volume, cubic meter. Cubic meter. which is m raised to power 3. Then number 3, we have speed. Speed is measured as meter per second. Meter per second, which is like this as its symbol. Then we have acceleration. Acceleration, the basic SI units will be meter per second squared. And here we have meter per second squared. For density, we have mass, we have kilogram per meter cube or cubic meter. Kilogram per meter cube. Kilogram per cubic meter. That is the derived quantities and their units with examples. Now, let's quickly look at the dimensional analysis. The dimensional analysis of the derived quantities. Now, when calculating the dimensional analysis, we put into consideration, I'll tell you now, dimensional analysis. We put into consideration M, L, C. M, L, and C are used to represent. These are used to represent the fundamental dimensions of mass in kilogram, dimension of the fundamental lengths in meter, and T, time in seconds. To find the dimension of any quantity, we make use of an equation that relates that quantity to quantities. You know. Yes, we relate that quantity to quantities that you know. For instance, look at the derived quantity, area. Area is measured by length times length. And if you look at length is in meter. Length is in meter, and that gives us meter squared. That is the derived quantity, area. And area takes its derivative from the fundamental quantities because it is a derived quantity. So we say that it takes its quantities and units from the basic quantities, which is the fundamental. Now, the dimension of area here will therefore be, the dimension of area will therefore be L squared, and that is the answer. For acceleration, for instance, let me make acceleration as an example here. Acceleration as a derived quantity is measured as distance, no, let's say velocity over time. Acceleration is actually defined as velocity, change in velocity per unit time. So acceleration, which is velocity over time, we have velocity as its unit to be meter per second, and now we have seconds here, and that gives us acceleration to be meter per second squared from the derived quantity. And so to get the dimension of acceleration, we say that m, which represents length, meter, which represents the length, therefore become L. Then seconds is here and seconds is here, and we have C, which represents the time in seconds. Then we say we have it here, we also have it here, so we have squared. Therefore our dimension becomes L T squared. Do we get that? That is the dimension analysis we are talking about. If a question is given to find the dimension of pressure using this notation m, x, l, this is a typical y question. M raised to power x, L raised to power y, and C raised to power z. And you are asked to find the dimension of pressure using the dimension of the quantity pressure to calculate the value of x, y, and z. What do you do? This is a question, a typical YEC question. Your m is raised to power x, your L is raised to power y, and your T is raised to power z. And here you are asked to use the dimension of the quantity pressure to calculate the value of x, y, and z. How do you go about this? Now, what you do, solution to this simple question. Pressure is actually calculated as force over area. And you know that force is mass times acceleration, then area down. Your mass is measured in kilogram. Your acceleration is your meter per second squared. Then your area is your meter squared. Now, how do we go about this? Pressure, which you have to find its dimension, will then become kilogram. This will take off this, and we are left with only m down. So we have kilogram per meter per second squared, and that will give us our pressure. Although the fundamental unit of pressure is force over area, which is Newton per meter squared. Newton meter squared. But in this case, finding the dimension, we say kilogram. Kilogram, which is represented by M, and your meter, which is represented by L, then seconds, C minus 2. Therefore, we say that the value of X, Y, and Z is, since we arrive at M from the analysis, the dimensional analysis of pressure, we arrive at M, L raised to power minus 1, C raised to power minus 2, and compare to X, our X will become 1, because the value here will be 1. Then our Y will be minus 1, and our Z will become minus 2. I hope you got the analysis. God bless you.